Hey, I actually closed the other window a little bit too soon on that last video, so I'm going to break this into two videos, but that's okay. So, um, I want to go over a couple types of problems that you're likely to see on the AP test that have to do with center of mass and momentum. So let's take a look at this one here. This is a very classic physics problem. So I have a 60-kilogram man standing on a 100-kilogram raft, 4 meters long, touching the edge of the pool. So the man is 3 meters away from the edge of the pool, and he's going to walk across the raft at 1 meter per second and stop when he gets to the far side of the raft. And these are the type of questions we might be asked about. So, when the man reaches the far side of the raft, how fast did the center of mass of the raft man system move? How far does the center of mass of the system end up from the edge of the pool? How far is the center of mass of the raft from the edge of the pool when the man gets there? And how far is the man from the edge of the pool? So we could be asking any one of these questions. Let's take a look at this. Let's start with the first one here. How fast did the center of mass of the system move? Well, it didn't, because there's no outside force acting on it. We're assuming that friction is ignorable. And so remember, I have an internal force. The man and the raft are the system, and they're putting a force on each other. So that can't change the position of the center of mass. So it did not move. Now, how far does the center of mass of the system end up from the edge of the pool? Well, it didn't move. So we just need to figure out where the center of mass of the system is. So what we're going to do is we're going to say, well, here's the edge of the pool. We're going to say uh, the the raft is 100 kilograms and its center is 2 meters away. So 100 times 2. The man is 60 kilograms and his center is 3 meters away. And so when I solve that, I'll get 2.375 meters. So that's where the center of the mass of this man raft system is. And that's where it's going to stay unless some external force acts on the system, which in this case it doesn't. How far away is the center of mass of the raft from the edge of the pool when the man gets to the far side? Well, now this is the tricky one, okay? So here's what we have to do here. We're going to say, all right, well, look, I know that the center mass of the system stayed 2.73 meters away. So in my center mass equation, I can put this in. Normally I'm solving for this, but this time I know that. What I don't know is where the center mass of either object is, but I can solve the center mass of one object in terms of another. So what I'm going to say is, well, I've got this 100-kilogram raft, and its center of mass ends up X meters away from the edge of the pool. I probably should have put that term first. Now, the person, their center mass, their mass is 60 kilograms, and I don't know where their center mass is, but wherever the center mass of the raft is, they are 2 meters closer because it's in the middle of the raft, and this person's on the far edge of the raft. So I can substitute in X minus 2, where X is the center of mass position of the raft. And then I use their two masses, and when I solve it, I'll get 3.125. So that tells me then that as this person walked this way, the center mass of the system stayed here, but the center mass of the raft moved this way, and the center mass of the man moved this way. So where is the center of mass of the man? Well, he is 2 meters closer to the edge of the pool than the center mass of the raft because the raft is 4 meters long. All right, and its center mass is at 2. So I basically take the new center of mass of the raft, which is 3.125, and I take away 2 because the man is 2 meters closer to the edge of the pool than that is, so he's 1.25 meters away. Now, these problems are tricky ones when you're asked, right? They're all predicated on the notion that the center mass doesn't change, but you got to do a bit of calculating that one little trick about saying, okay, I'm going to use X to be the new center of mass of the raft and X minus half the length of the raft to be that of the man. It's a little bit tricky. So hope if you get one of these, it'll be a qualitative question. But if you get this, you can work your way through it. It just takes time. A more likely scenario you'll get is something like this. So I have a 200-kilogram object and a 60-kilogram object that are connected by a cable. A lot of times they do this with spaceships because that way there's no external force. I'm just going to say sliding across a frictionless surface at 10 meters per second. A winch, which is a device that coils up a cable, in the 60-kilogram object begins to reel in this cable. All right, so it's bringing the two objects closer together with a force of 60 newtons. After the cable is operated for 2 seconds, how fast are the objects traveling? So how fast is the center mass of the system traveling? How fast is the 60-kilogram object traveling? And how fast is the 20-kilogram object traveling? Well, let's see what we've got. So the center mass of the system is still traveling 10 meters per second because there's no external force acting on it. So it doesn't change its motion. They will ask you this so many different ways on the test. And the answer is always this: if no outside force acting on the system, we'll later deal with outside forces acting on it. But if no outside force acted on it, its motion didn't change. It was going 10 meters per second to start with. I don't see any outside forces acting on it. The center mass still moved 10 meters per second. Let's try the other objects. Well, how about the 60 kilogram object? Well, the 60 kilogram object, here's its mass. I'm just going to use this equation here. And so there was a force acting over time. So there's a change in its momentum. So there's a change in its velocity. So I'm going to substitute. I'm going to say, well, the force was 60 newtons. I probably should use a different value. Okay. The time was it operated for 2 seconds. So I'm going to put 2 here. The mass of the object was 60 kilograms. The final velocity is what I'm trying to find, but minus the initial velocity. So it was moving in the positive direction at 10. So I simply solve for the unknown. I get 12 meters per second. And if you think about it, it makes sense. We were going at 10 when the winch basically caused this cable to apply a tension force. That tension force is going to pull this object in the negative direction, but it pulled this object in the positive direction. So this object had to end up going faster. A lot of times they'll ask this question qualitatively, just what should happen to the mass of this object, and what should happen to what should happen to the velocity of this object, what should happen to the velocity of the center mass of the system. And then if we think about this one's pulled in a negative direction, so it should slow down. So in this case, I'm going to use the same thing. So it's the same force, 60 newtons, but you've got to be careful. This 60 Newton force is acting in the negative direction, but acted for 2 seconds. This is a 20 kilogram object that I'm looking for its final velocity, and it started off initially traveling in the positive direction. Remember, because it's final minus initial, and its initial was in the positive direction. So when I solve this, I get 4. And it makes sense that it slowed down. So it was traveling at 10. A negative force acted on it. It had a smaller mass, so it's changed its velocity more. It's now going 4. Pretty cool. All right, thanks for watching.